Hello! In this video, we are going to prove the following theorem. For every complex number a plus 0 is equal to a. Now in this series, we are looking at a list of axioms for the complex numbers. These axioms come from MetaMath, and I'll leave that list of axioms and a link to MetaMath, which contains those axioms, in the description below. So let's remind ourselves what we're working with. So we have a set C, called the set of complex numbers. We are given a subset of the complex numbers, R, called the set of real numbers. And we're given three elements of the complex numbers, 0, 1, and I. We're also given two binary operations on the complex numbers, addition and multiplication. So given any two complex numbers, a and b, a plus b is a complex number, and a times b is a complex number. And finally, we are given a relation on the set of real numbers, called the less than relation. So given any two real numbers, a and b, it might be the case that a is less than b, and we write that like this. Otherwise, a is not less than b, and we write that. And from here, we have a list of axioms for the complex numbers, and that's in the description below. Now, in proving this theorem, we're going to be using the following axioms. We're going to be using axioms 1 through 6 and axioms 10 and 11. Actually, there might be one that isn't being used, but let's just remind ourselves what these axioms are. Axioms 1 and 2 tell us that the sum of any two real numbers is a real number. The product of any two real numbers is a real number. Axiom 3 is the commutative law for multiplication. So given any two complex numbers a and b, this equality is true. Axioms 4 and 5 are the associative laws for addition and multiplication. So given any three complex numbers a, b, and c, these equalities hold. Axiom 6 is the distributive law. So given any three complex numbers a, b, and c, this equality holds. Axiom 10 tells us, given any real number a, there exists a real number x such that a plus x is equal to 0. Axiom 11 tells us, given any real number a that is not equal to 0, there exists a real number x such that a times x is equal to 1. Now, we're also going to be using some facts that we have proven from our axioms. For example, we have proven that 0 is a real number. We have proven that 1 is a real number. We have also proven the left cancellation law of addition for real numbers, which says the following. Given any three real numbers a, b, and c, if c plus a is equal to c plus b, then a is equal to b. We've also proven that 0 plus 0 is equal to 0. We've also proven for every complex number a, 0 times a is equal to 0. Since multiplication is commutative, we could flip that around. So we also have, for every complex number a times 0 is equal to 0. We've also proven for every complex number a times 1 is equal to a. Right? And we could flip that around as well. For every complex number a, 1 times a is equal to a. We've also proven that 1 plus 0 is not equal to 0. So, now, with this in mind, let's prove for every complex number a plus 0 is equal to a. To start out the proof, let's give ourselves an arbitrary complex number a. And from here, we're going to show that a plus 0 is equal to a. Now, first of all, since 1 is a real number, we can apply axiom 10. So in that case, there must exist some real number, I'll call c, such that 1 plus c is equal to 0. Now, remember, 1 plus 0 is not equal to 0. And since 1 plus 0 is not equal to 0, we can't have c equal to 0. Because if c was equal to 0, this would tell us 1 plus 0 is equal to 0, contradicting that 1 plus 0 is not equal to 0. So we must have c is not equal to 0. So c is a real number that is not equal to 0. So we can apply axiom 11 to the real number c. In that case, there exists some real number, I'll call y, such that c times y is equal to 1. Now, observe that 1 plus c is equal to 0, right? That's what we have here. But remember, we've proven that 0 plus 0 is equal to 0. And now let's replace this first 0 with 1 plus c. And then by the associative law of addition, we can move these parentheses around the c plus 0. So we see that 1 plus c is equal to 1 plus c plus 0. Now, we're just working with real numbers here. So we're in a position where we can apply the left cancellation law of addition for real numbers. We cancel out the ones, so we're left with c plus 0 is equal to c. So we're going to use this to show that a plus 0 is equal to a. So now we observe the following. So a is equal to a times 1, right? We know for every complex number a times 1 is equal to a. But then we're going to replace this 1 with c times y. Well then, let's replace this c with c plus 0. This is what's going to allow us to obtain a plus 0, the fact that we've rewritten c as c plus 0. Because now, let's first apply the commutative law for multiplication. We can flip c plus 0 and y around. And then applying the distributive law, we can distribute y across this parentheses. Well then, applying the commutative law here, we can flip yc to c times y. And then we know that any complex number times 0 is 0, so that's just 0. Now, cy is equal to 1, right? That's what we have here. So then we distribute a across this parentheses. We get a times 1 plus a times 0. But we know for every complex number a times 1 is equal to a. So a times 1 is a. But we know that any complex number times 0 gives us 0, so a times 0 is 0. So we're left with a plus 0. So this chain of equalities shows a plus 0 is equal to a. And that's it. So this completes the proof. And so yeah, that's pretty much it for this video.